A polynomial of degree n and leading coefficient a sub n is given in this form over here. So we call this expanded form because we have a bunch of terms that are added together. There's no parentheses and nothing is factored. So what I'd like to do is take this very abstract looking definition and just write down a few examples of polynomials because ultimately they're very easy to describe. So maybe a simple example would be something like y is equal to 5x cubed minus 2x squared plus 3. Here we have x's to positive integer powers. There's coefficients in front of some of the numbers. I skipped over x, but that's okay because you could say that that coefficient was equal to 0. So essentially, here's a very basic example of a polynomial. Now, there's another term in here, which is the degree of this thing. Here I say the degree is n, which refers to this largest number that appears here. So the degree of this polynomial is equal to 3 because it's the largest exponent that appears within the equation. There's also this leading coefficient, which I'll write as a sub 3, and that's equal to 5. So maybe just a couple of other examples. You could have something like y is equal to negative 1/2 x to the 201st power plus x to the 70th. Here the degree is equal to 201, and then the leading coefficient, which would be a sub 201, it's just that negative 1/2. And perhaps just one more. How about y is equal to x times x to the 5th minus x cubed plus 2. So this is a polynomial, but currently the way this one is written, it's not an expanded form because here a bunch of terms are added together, nothing is factored, but this one is factored. If you wanted to write this in expanded form, it'd be very easy to do. You would just distribute the x into the parentheses, which would change the equation to y is equal to x to the 6th minus x to the 4th plus 2x. It's at this point where you can say, okay, the degree is actually equal to 6. So it would be a mistake to say the degree is equal to 5 because this is not completely multiplied out. Here we have the largest exponent of 6, and the leading coefficient, a sub 6, is equal to 1. So maybe it would be good to look at some things that are not polynomials. So an example would be something like y is equal to 12x to the 4th plus 3x cubed plus x to the negative 7. So here I have a negative exponent, which falls out of the definition of what we have here. All the x's are to the first, second, third, fourth, and so on, but they never become negative numbers. So this is not a polynomial. Something else that wouldn't be a polynomial is if you had, I don't know, maybe something with a square root of x in it. So like this, for example, is not a polynomial because of this term right here. And for that matter, something like, y is equal to the absolute value of x squared minus 5x plus 14. Like that's not a polynomial either, and the reason is because of the absolute value that surrounds this expression. So here are 3 examples of things that are not polynomials. Other things would be like if you had y is equal to x to the 5th minus 1 over x. Here, none of the variables appear within a denominator, so that's not a polynomial. And I think that should really do it, just kind of looking at these few examples here. So here we have polynomials. These are not. Now that we have defined a polynomial, the second thing is going to be to identify the graphs of these things, like what do they look like? I put this fact up at the top about the end behavior of a polynomial. So if you look at these 2 graphs, these are both graphs of polynomials that we'll identify in a second. When we talk about the end behavior, that means what is the end of the graph doing? So we're ignoring like what's happening in the middle and we're focusing on the ends of the graph. Like this one goes up and this one goes down. Over here, when we talk about the end behavior, again, we're ignoring what's in the middle of the graph and focusing on the ends of the graph. Notice that these both go up. So the distinction that we're going to look at here is between even and odd degree. If your polynomial goes up on one side and down on the other, this has to be of odd degree. And if your polynomial goes, let's say, up on both sides, this is going to be even degree. So the reason is, like, if you raise something to an x squared or an x to the fourth, all the negative numbers become positive numbers, which is why it goes up on both sides. Whereas if you were to cube a graph or raise it to the fifth power, the positive numbers stay positive, but negative numbers stay negative. So once we have this distinction between these two different types of graphs, we can identify these two equations and even check our answers by using a graphing calculator. So let's start with this one here. Y is equal to 5x to the fourth minus 4x cubed minus 2x squared plus 3x minus 1. Pretty complicated polynomial. But if you focus on just this portion here, I see that the degree of this thing is equal to 4. So for this first polynomial, if I focus on this one, the degree is 4. The leading coefficient, which would be a sub 4, is equal to 5, but it's really the degree I care about. If I look at this other polynomial over here, the degree is coming from this term, this 3x to the fifth, so the degree here is equal to 5, and it has a leading coefficient of 3. This is all the information that you need to identify which of these two polynomials is which. Because this has a degree of 5, it has to be odd degree, so it's referring to this graph here. So let me copy that down below here. We have y is equal to 3x to the fifth minus 3x cubed minus 2x minus 1. So you can check this by plugging it into your graphing calculator, but you should see a picture that looks like this. So again, all we're focusing on is this thing right here, this 3x to the fifth. Now, these other terms that appear within the expression, what they do is dictate what happens in the middle of the graph. So the 3x to the fifth means it goes down on this side and up on this side, and it's these terms that kind of connect it in a strange way from one end of the graph to the other. So likewise, if you focus on this graph over here, the fact that the degree is even means it must be this polynomial, which I'll write down. So this one is y is equal to 5x to the fourth minus 4x cubed minus 2x squared plus 3x minus 1. And again, all I'm focusing on is this portion of the graph. This 5x to the fourth tells me, oh, a fourth degree means it's got to go up on both sides. And it's these extra terms at the end which determine what the graph does in the middle. So let's try this idea out in just one last example where now we have 4 different polynomials and we want to correctly identify them to the graphs. Now I'm throwing in one extra idea here. Like if you kind of quickly just scan the 4 graphs that we have, like here this one goes up on both sides, so I know it's got to be even degree. And this one, it goes down on both sides. It's also even degree, but this one's like upside down compared to this one here. This is where the leading coefficient becomes really important. If the leading coefficient is positive, I'll have up on both sides. Whereas if you have a negative in front of that leading coefficient, it's going to flip the graph upside down and make it go down on both sides. So again, here we have 4 different graphs that we want to identify between these 4 functions up here. Let's start with A. Y is equal to negative 10x cubed plus x squared plus 12x plus 4. All I want to focus on is this negative 10x cubed. These extra terms determine what happens in the middle of the graph. All I need is this. Okay, the degree is 3, and the leading coefficient is negative. So I need something that is going up on one side and down on the other, but it's going to be flipped from what we saw in the previous example. It can't be this graph, and it can't be this graph, so we're left between this one and this one. So this goes down on this side and up on this side. I actually would like the reflection of this, which is this graph over here. So what we have is that this has to be the polynomial for A. And the reason for this is the degree is odd, but also the leading coefficient is negative 10. The fact that it's a negative number flipped the graph upside down. All right, let's move on to B. This is 0.1x to the fourth. So we have a 4th degree polynomial, which means it can't be either of those. It has to be this graph or this graph. And the leading coefficient is a positive number, so it's going to be this graph here. So this is B. And the reason for this is here the degree is 4, which is even, and that leading coefficient is a positive number. Maybe I'll go back to this one and say, oh, well, that's a negative number, it flipped the graph upside down. Moving on. For C, we have 0.5x to the 7th. So this has odd degree. It can't be this. It has to refer to this graph down here. And here we have this positive coefficient, means the graph isn't flipped upside down. So over here, this has to be C. Here the degree is equal to 7, and that leading coefficient is a positive number. By process of elimination, clearly this has to be the graph of D, but it makes sense. Here you have an even degree, which is x to the 6th, and this negative coefficient flips the graph upside down. So I'll write down that this is D, and the reason is the degree is equal to 6, and it has this negative leading coefficient.